Okay, so in this chapter, we'll talk about static equilibrium and elasticity. Sort of unrelated topics, but generally in all physics books, they get lumped together. Okay. All right. This part, this is two equations, and that will become a whole course if you're a civil engineer, course of statics. Just two equations will become a whole course. Okay. And so let's understand this term. What does static mean? Yeah, so it's at rest. What does equilibrium mean? So you think it means the same colloquially. So equilibrium means acceleration is zero. Okay, acceleration zero doesn't necessarily mean you're at rest. Acceleration zero just means your velocity is constant. Okay, and so what we want to do is, we want to say, so that's why we added this term, static equilibrium. So your acceleration is zero. That means all the net force acting on you is zero. And it also means alpha is zero. Okay? Alpha, what is alpha? It's angular acceleration. Okay? And then on top of that, you want this to be static. Okay? So in your life, you see, so here is the object leaning against the wall. Okay? As you climb up the ladder, what is it that you want? You want this thing not to move. It needs to be in static equilibrium. Okay? Here's the structure. You drive across it, and what do you want for the structure to be? In static equilibrium. Okay? All right, as you're driving across it, what happens is these cables stretch. Okay? And when you drive away, what do you want to happen to the cables? Go back to its original shape. That is elastic behavior. Okay? All right, so you see both of those ideas in this picture. Okay, so now let me, we've done this before. So what are the conditions for static equilibrium? So let's figure it out on a simple case. Okay, so let's say if you have a point object, I apply, and you've done this in lab, I applied 3 forces on this guy. What needs to be true for this object to be at rest? That's right. Okay, so the sum of these forces need to add up to 0. Okay, so that was for a point object. What about for an extended object? Okay, as long as these forces are going through the center of mass of the object, okay, that condition is sufficient. Okay, even for extended objects. Okay, but now let's apply forces to an extended object. Okay, so like I said just now, this will be in equilibrium. Okay? So now we'll apply, so the sum of these two forces, F1 plus F2, F1 plus F2 is 0. And so it's in equilibrium. But now let's change something. Yeah, so now what I'll do is, all right, still the same two forces. Still this condition is true. They're adding up to 0. But now, is this guy going to be in equilibrium? Is this going to be at rest? What will happen? It'll spin. Okay, now the sum of the torques is not 0. Okay. So for an extended object, to be in equilibrium, you need these two conditions. The sum of all the forces acting on the object should be 0, and the sum of the torques of all these forces need to add up to 0. And these are the two conditions you need for static equilibrium. Okay? And that's a whole course. That'll become a whole course. So just those two equations. Okay. You guys understand? So if you have a point object, all you need is this condition. But if you have forces acting on an extended object, you need these two conditions for it to be in equilibrium. Okay? All right, so that's the first part of the chapter. And so let's go over that. All right, so what this diagram is showing you is, so let's say you're getting ready to bowl, and when your arm is at rest, this is the weight acting. So we are showing you all the forces acting on this object. Here's the weight of the bowling ball. Here's the weight of your arm. Here's the tension in the muscle, which is pulling up like that. This bone is pushing you down like this, okay? So in that diagram, here are all the forces acting on your arm. So here's your arm. There's the bowling ball. They ignore the mass of this bone, but and this is the bone pushing down. And that force should be here. And this is the tension acting on it. Okay? So for this arm to be at rest, the sum of all those forces should be 0, and the torques of all those forces should be 0. Okay? All right, so we'll look at that. Okay, now let's start off by defining center of gravity. So if you have an object like this, the center of gravity is the point where the weight, the gravitational force of the object acts on that object. That is the point at which the weight of the object acts. Okay? All right, now let's say, so we saw a related concept earlier in the chapter, okay, in one of the previous chapter. Let's say this is a square plate, metal plate of uniform density. Its center of mass was at its geometric center. Okay. Now, if this is a small plate, its center of gravity is also right there. Yep. Now, if it were a huge plate, let's say the size of, if it were the size of from here to Jacksonville, and you stand it on its top, then its center of gravity might be slightly lower. Okay? So only for very, very huge structures, ouch. Only for very, very huge structures will the center of gravity and center of mass be different. Okay? And the center of gravity will, of course, be closer to the center of the earth. Okay? But for most man-made structures, the center of gravity and the center of mass will be the same point. Okay? So let me give you the definition of that. Okay? So the center of gravity, here's how the center of mass is defined. So here's a structure. You break it up into little pieces. And the x-coordinate of the center of mass is the mass of this little piece times the x-coordinate of that piece, then plus the mass of the second piece times the x-coordinate of the center of mass. And you add up all the pieces divided by the total mass. The definition of center of gravity is, okay, you instead of the mass, you take the weight of that piece. And the weight of that piece is mass times the gravity at that location. Acceleration due to gravity. Plus the weight of that piece, times x2. Now look at this formula. I've written G1 and G2 as different quantities. What is the acceleration due to gravity in this room? What is it near the ceiling? What is it at the top of the building? I'm sorry? Yeah. What if this was a 100-floor building? What would be at the top of the building? I'm sorry? It does decrease, but it would not noticeably decrease. It would be 9.8 at the top of the Empire State Building. It's 9.8 at the top of Burj Khalifa. Okay, so as long as you're not dealing with extremely large structures, all this will be the same, and that'll cancel out. But if you're dealing with very large structures, let's say you make a space ladder or something like that, then the center of gravity will be different, and the center of gravity would be slightly below the center of mass. Okay? All right, so for practical purposes, for our cases, if you're going to be civil engineers and stuff like that, center of mass and center of gravity are the same. Okay? So for very large objects, say Mount Everest, will the center of gravity be below the center of mass? Okay, and the reason we want to know the center of gravity is that's where the weight of the object will act. Okay, and that's why you need to know that. And we need to know where the weight acts because you'll need to calculate the torques of that forces. Remember, what are the two conditions for equilibriums, for static equilibrium? We said that the sum of the forces must be equal to 0 and sum of the torques of these forces must be 0. Okay, so when you're calculating the torque due to gravity, you need to know where gravity acts, and it acts at the center of gravity. Okay. This is just a pretty picture, and you can do this with Jenga tiles at home. What is pretty about this?
It doesn't fall over just by being on the edge.
I'm sorry?
It doesn't fall over just by being
You see,
on the edge.
yeah, see this thing? It's over the edge, and you can do this. So you can make these structures, and they're not cemented. So, I mean, if you design a building and you like this overhang, you could make this. All right, what's going on? All right, so you see, this guy, he won't topple over as long as his center of mass or center of gravity, now that we're talking about, but they're the same thing, is behind the edge. So you see for the top structure, the center of mass or center of gravity is behind the edge. That is the criterion. All right, for these two guys, if you don't want these two to topple over, the center of mass of these two guys is there. That's behind that edge. If you don't want these three to topple over, the center of mass of these three guys, which is there, see, is behind the edge. And that's the criteria. And actually, you can make it as high as possible, and you can have this thing extending quite far. So if you don't want the wind to blow, or just, you can just put hooks and stuff, and this can be a pretty structure. You saw this device, okay? Again, what is true? The center of mass of this structure is above this footprint. Okay. So the conditions for equilibrium, for static equilibrium on an extended object is the sum of the forces acting on the object should be 0, and the sum of these torques should be 0. Yeah. For point particles, all you need is this condition, okay? And even for extended objects, as long as all the forces are going through the center of mass, this condition is enough. But if forces are not going through the center of mass, you need this additional condition for an object to be in static equilibrium, for an extended object to be in static equilibrium. Okay, so these are the two conditions you need. Okay, now here we'll keep things simple. So what we'll do is we'll have all forces acting in a plane. Okay, so let's say if all the forces are acting in a plane, in the xy plane, you want the x component of the forces to add up to 0 and the y component of the forces to add up to 0. And it'll turn out that the torques of all these forces are in the z direction. Okay, and so the torques along the z direction should add up to 0. So all you have is you have three conditions that you want to satisfy. Okay. Now when you get to your engineering classes, then you'll consider forces in three dimensions when you have structures and stuff like that, and then you'll have torques in three directions. So you'll have 6 equations. Okay. So when you consider the forces on the bridges and stuff like that, or on a building, you'll have forces in three directions and torques in three directions. Okay, 3 component torques. All right, so let's look at the kind of problems we will solve. Okay, so here's a structure. Okay, so here's a scaffolding, and what does this fellow want about the scaffolding? He wants to be able to put weights there. He wants to be able to walk anywhere he wants on the scaffolding and stuff like that. Okay, so the forces on this structure will change. Okay, as he's walking back and forth, what is happening? You don't want this moving. So you'll see that the tension in this string changes. Okay, so here's the tension. It's pushing the scaffold against the wall. The wall is pushing back on the scaffolding. Okay, so as he walks back and forth, the tension changes, this reaction force changes, and so on. Okay, so the forces are changing on this, and under all those circumstances, what is it that you want? You don't want this darn thing to move. Okay? So that's the kind of analysis you'll be doing. Okay? So we'll call this the free body diagram. So here's the scaffold, and you want this to be in static equilibrium. So let's draw all the forces on the scaffold. Okay, the tension in the rope, the tension in this wire is applying a force in that direction. Here the weight of the person, here the weight of the scaffold itself. And see, this tension is pushing this scaffold against the wall, and the wall is pushing back on the scaffold. And there's the reaction force of the wall. Okay. So those are the 4 forces acting on the scaffold. Okay. And what is it that we want? We want the sum of these forces to be 0. And the torques of these forces to be 0. All right, so here's a punchline. So what is the torque of a force? It's Ri times F cross Fi. What is Ri? What is this? That is the position of this force from this point, let's say, if you're calculating the torque about that point. Well, what point do you calculate the torque about? You can calculate it about any point. Okay? So here's a theorem. If the sum of the torques is 0 about some point, and here's the amazing fact, it will be 0 about every point. You can calculate the torque about any point. Okay? So if the sum of the torques of a bunch of forces is 0 about some point, then it'll be 0 about every point. Okay? So that's a good one to remember. Okay? So when the net torque is 0, the choice of axis is arbitrary. Okay? The choice to calculate the torque about any point about a point is arbitrary. So here's the trick that you need to remember. So let's say we are doing this problem, And in this problem, they ask you to find the tension, and they don't ask you to find this reaction force. So what do? You calculate the torque about that point. Okay, and that force is always eliminated, and you don't care because you didn't need to find that force. If in a problem you don't need to find the tension, then you calculate the torque about that point. Okay. So what you do is you want to be smart about the choice of axis. Okay, since if the sum of torque is 0, then you can calculate it about any point. Okay, so and we'll do that when we do problems. A force that acts along a line passing through the axis produces 0 torque. Okay, so what this is saying is, okay, in this problem here is the tension. That tension has been broken up into two components, this component and that component. You can think of this single force as being replaced by this force and this force. Okay, and if you're calculating the torque about this point, see, this guy will have 0 torque because his moment arm is 0. Only this guy will have a torque. Okay? And these two guys will have 0 torque. This guy will have a torque, clockwise torque about that point. Okay. All right, so you just need to remember all those little tricks. Okay, so here's that problem again. You're holding on to a bowling ball, and what they show is, so here's the weight of the bowling ball acting, and there's the pivot point. You're calculating the torque about that point, and this length is 35 centimeters, and this distance is 3 centimeters. Okay, so just a quick calculation. So in this case, okay, if the arm is at rest, that means the sum of the torques is 0. Okay. This weight about this pivot point is turning the arm clockwise. The torque is negative, and this torque, this force, is turning the arm counterclockwise. That's a positive torque. Okay, so force times D minus mg times L is 0. So force is L by D times mg. L is 35 centimeters, D is 3 centimeters. So that's almost, this factor is almost 12. Look at this amazing fact. Okay, so to lift this bowling ball, your muscle is applying a force, a tension of 12 times the weight of the object. Sounds like a pretty bad design to me, right? Why is that? Yeah, so why would you design it then? I thought you were pretty smart.
I don't make
What's that?
I said I don't make the rules, I just follow.
You don't make the rules. All right, so work is force times distance. The thing is, your muscles have to be strong because they cannot contract too much. Okay, the contraction is very small, so that's why you have to be able to apply large forces to be able to do any significant work. And so this is equal to output work times output distance. Okay, so you apply very large forces so you can lift small loads a large distance. All right, so here's the ladder problem. Again, as you climb up the ladder, you don't want the ladder moving on you. Okay. So generally in this ladder problem, what you do is, so the ladder is leaning against the wall, and we consider ladders leaning against smooth walls. So this wall can only exert a force in this direction. There's that force. Okay. There's the normal force of the ground exerted on the ladder. There's the weight of the ladder. Okay, and let's say if you're climbing the ladder, then we'll have to put your weight, add your weight as well there. Okay? And what can happen is as you're climbing up, the ladder will slip and want to slip in that direction, and that's why you have a boot there, okay, which is providing you friction forces. Okay? So those will be all the forces acting on the ladder, and you make sure that this doesn't slip and so on. Okay? So if you invented that boot, you probably are a millionaire by now, if you have a patent. And then what you did was you put the heaviest person on top of that ladder and made sure that this friction force was large enough. Okay? That's what you did. All right, so that was the equilibrium part. That was the first part of the chapter. Okay? Some of the forces on an extended object need to be equal to 0, and some of the torques of these forces need to be 0 for the object to be at rest. Okay? Now we'll consider elasticity. Okay, so we'll quickly go over elasticity. Okay? And like I said, so you want elastic behavior for the following reason. Let's say you drive over this bridge, these cables will stretch, okay? And then when you drive away, you want the cable to go back to its original shape. That's elastic behavior. And how often do you want this to be done? Millions and millions of times, okay? Infinite number of times, if possible. But of course, that doesn't happen. Most of these structures have, I mean, this bridge has been there almost 100 years, but you know, there are other structures that don't last that long. All right, so we'll do a simple model. A solid like this can be modeled like that. So here are the atoms, and the interatomic forces are modeled by springs. Okay, so let's say you clamp this thing, you tug on this metal object, you pull on this. What you're doing is when you're pulling on this, you're stretching all these springs in between. All right, so let's say I'm pulling on this. I'm going to just show you a single layer. Okay, so what did you do? You stretched all these springs, and all these springs, this guy is pulling him back, this guy is pulling him back. Okay, so you grabbed hold of this top layer and you apply this force. Well, the question is, how much did these springs stretch? Okay, if you applied 100 pounds, all these forces added up to 100 pounds. They're pulling back, okay? My friend, hello? Yes. You're disturbing the class. You just can't walk in and walk out just like that. What do people think? It's their grandma's house here? No respect for anything. All right. So you pull with a force of 100 pounds. The springs stretch so that this force add up to 100 pounds. What happens if I pull with a force of 200 pounds? I'm sorry? So these springs have to stretch more, and they add up to 200 pounds. Okay. So this layer is being pulled with a force of 100 pounds. They're being pulled back. What is this layer? That layer is also, see, this spring stretches. They're pulling these guys. That is also being pulled by 200 pounds and so on. Okay. Anyway, so you guys understand that. Okay. So you double the force, the stretch doubles. Yep. You have elasticity. What does the word elasticity mean? If you remove this force, the springs have to go back to their original shape. Okay? And that's elastic behavior. Okay? If the springs don't go back to, let's say you apply a large enough force where the springs don't go back to their original shape, then you have deformed the object. Okay? If you deform this object, now the bridge is sagging, and you don't want that. Okay? So what is it that you do as a designer? Okay, so this graph shows you. Okay, what this graph shows you is the following. So this is the force you're applying, force divided by area of cross section. That's stress. Okay, so what this shows you is for this material, as long as so this is the yield point. This is the elastic limit. If you apply a force greater than that, the object permanently deforms. Okay. So if you're a civil engineer on all those guys, you're making sure that you don't apply stresses greater than that. Okay? And when you remove the stress, the object goes back to the original shape. Okay? So you build in plenty of room for error. Okay? You never go anywhere close to that. Okay? Well, a way to make sure that you never go anywhere close to there is, how do you do that? You just put 1,000,000 cables, but then it's getting more expensive, so you're trying to balance between costs and, and it probably would look ugly too, but, so that's what you're trying to do. All right, you guys understand that? All right, here's another thing I want you to understand because I'm going to zip through these slides. Okay, this is a tensile stress. A tensile stress is when you're lengthening the structure. This is a compressive stress. Okay? It turns out that a lot of materials are strong under compressive stress. Okay? They're weaker under tensile stress. Your bones are stronger against compressive stress than tensile stress. Okay? Concrete is almost 10 times stronger under compressive stress than tensile stress. What does that statement mean?
If you pull on it, it'll snap. If you press on it, it won't break.
So, yeah, you need almost a 10 times compressive force to break it. All right, what does that mean? So, if you're building any structure, what you're making sure is, if your structure is to bear a large force, it had better be a compressive force. Smaller forces you can let tensile stresses handle that. Okay? Large forces had better be compressive forces. Okay, let me show you that to you in this example. Okay? All right, so here's the structure. Let's say there's the bridge. And I'm just going to make up some numbers. So let's say we have to support 1,000,000 pounds. Okay. So the bridge weighs 1,000,000 pounds. Okay, so so what I'm going to do is I'm going to throw in 1,000 cables. Okay, each cable now is bearing what? 1,000 pounds. So each cable is bearing 1,000 pounds. Okay, so this cable is lifting 1,000 pounds. Okay, so the cable is under a tension of 1,000 pounds. Okay, and so the cable is actually stretching. So what I've drawn here is the cable is stretched and it's pulling on the rod with a force of 1,000 pounds, and it's pulling on this cable with a force of 1,000 pounds. All these guys are pulling down on this cable. Okay. So all these forces end up pulling this cable like that, which is, what is it doing? Which is pushing down on the structure. Anybody can guess what that is? What is that compressive force? Okay, so you're lifting up 1,000,000 pounds, so eventually these forces have to be 500,000 and 500,000 pounds. So this compressive force is 500,000 pounds. So you see this structure, which is bearing the largest load, half the weight is a compressive load. These cables are bearing tensile loads, which are much smaller. Okay? So that's why you had so many cables. All right, so that's what goes into these things. Okay, so compressive strengths are greater than tensile strength. Okay, so here's the table: compressive strength, tensile strength. What this is in megapascals. That's force divided by area of cross section of the column. Okay. And let me show this for concrete. So here's concrete, and you see tensile strength is 2 megapascals, and compressive strength is 20 megapascals. So it takes a 10 times greater stress to compromise a concrete structure compared to tensile stress. Okay. For bone, it's about 50% stronger under compression. Okay. So cast iron, which is what you use in structures, it's about 3 times stronger. Okay. All right, do you guys understand that? Any questions on that? All right, so when this guy is lifting, so if this bar were to crack, you see as the bar is bending, the top portion is being stretched and the bottom portion is being compressed. So if at all this were to develop a crack, that's where it would develop a crack. Okay. Remember, under tension, under tensile stress, you're lengthening it, that's where it would develop a crack. All right, so this kind of stuff you face in your structures as well. Okay, so here, let's say this is the span of a bridge. If you drive across the bridge, the bottom portion stretches, the top portion compresses. So in a bridge, that's where you would develop cracks. So how do you fix that? So here's how we fix it. Okay, so that's where pre-stressed concrete comes in. Okay, what you do is you take these bars, metal bars, and put them on vices and stretch them. Okay. And they're under large tension, then you pour concrete on top of it. And once the concrete dries, you let go of this tension. Okay. And now, what happened? Remember that bar was stretched, and when you let go of the tension, it compresses it. So now you have pre-stressed concrete. Okay. And now when a car goes by, it just goes back to its original length. It's just, okay. And then you can put a heavier load, and then maybe it'll stretch some more. Okay, so it's become much stronger now. It can bear much higher loads. Okay, so these are pre-stressed concrete. Okay, so this was rods under tension, and so when there's no cars, it's compressed. It's not its natural length; it's smaller. Okay, but concrete is fine with that. Okay. All right. Now here's another kind of deformation that you'll see. So let's say you put this cube underwater. The forces on it make the volume go smaller. Okay, so this is a volume deformation. Okay. So, all right. Now in this business, you have to understand 2 terms: stress and strain. Stress is equal to the external force acting on the object per unit area. So stress is force divided by this area. Okay? So in this case, here, in this case, stress would be this force divided by the area of cross section. Because stress is the force per unit area. Okay. And strain is defined as the percentage deformation. Okay. So in this case, the rod stretched that much divided by the length of the rod. So this gives you the fractional change. Okay. And so if you have a metal, this will be less than 1% and so on. Okay. If you have a rubber band, you can have a rubber band and stretch it almost twice its length. Okay. So this can be as large as 1. Okay. But for metal, it's 0.01 and so on. Okay. So anyway, that's strain. So that's what these terms are, stress and strain. Okay. So strain is a measure of degree of deformation. We define 3 kinds of elastic moduli. The 3 kinds of deformation we study, encounter are, so let's say the dimension of this, there's the structure, you're applying a tensile stress, and the length of the object increases. Does any other dimension change for this object? Yes, its width will decrease, but that decrease is so small that this is the most significant change, and that's what we'll look at. Okay, so we look at that deformation. We look at volume deformation. Okay, and then here's the shear deformation that you see. Okay, so here's a structure, and you apply shearing forces. Okay, and the deformation is like that. For instance, when you bend down and pick up a weight, that's how your discs deform. Okay? And of course, you don't want your disc to rupture and stuff. Okay? So we'll look at elastic moduli. Elastic moduli. So when an object is undergoing this kind of deformation, the elastic modulus, relevant elastic modulus, is called Young's modulus. This is bulk modulus, and this is shear modulus. Okay? Elastic modulus is the stress, force divided by the area, divided by the strain. Okay? All right, so there are 3 elastic moduli. Young's modulus, okay, when a solid is undergoing its change in length. Shear modulus measures the resistance of deformation of parallel planes. Okay? And bulk modulus measures the resistance of solids to change in volume. Okay? These moduli are large for stiff materials. Stiffer the material, larger those numbers are. Okay? So, of course, if you're building bridges and stuff like that, you want stiff material. Okay? And so on. Okay. So Young's modulus is when the predominant deformation of an object is in the length. That's the Young's modulus. It's tensile stress, force divided by the area of cross section, and the tensile strain is the change in length divided by the original length. What are the units here? See, this strain is dimensionless. Length divided by length, that's dimensionless. Only this guy has units, force divided by area, Newton per meter squared. Okay? And this is also called pascals. These are the units of pressure as well. Okay? So for most materials, you plot these stress versus strain curves. Okay? So what this is showing you is you're applying this stress, and this is how much it deforms. Okay? So as long as you're this is proportional limit. What this means is if you double the stress, the strain will double. If you double the stress, as long as you're in linear region, the length will increase in length will double. Okay, that's what this means. Here you've gone out of the proportional limit region. Okay, this is the yield point. Okay, that's if you go beyond that point, the shape changes permanently. Okay, so for most materials, you'll have curves like this, and if you're making a living using these curves, what you're doing is you're making sure that you're using these materials in structure, you're being somewhere here. Okay? So if you go over, if you have driven over that bridge on 9A in Jacksonville, a beautiful suspension bridge, okay? That's how you decide how many cables you throw in, okay, on that bridge. You want the stress to be somewhere there, okay? All right, so when you use a pair of scissors, what you're doing is you're applying these forces, shearing forces, and then you're fracturing, making those layers of atoms slip. Okay? So that's how you cut stuff. So shear modulus is force over area, and the strain is how much did this surface move relative to this surface and how far apart are they. The further apart they are, the greater the shift will happen. Okay? Bulk modulus, when you apply pressure like this, the volume decreases. Okay, so again, there's the bulk stress, and there's the change in volume divided by that. Why is that minus sign there? Can you figure that out? Why is that minus sign there? What is happening to the change in volume? It's decreasing, it's negative. So we want the bulk modulus to be positive, so that's why we threw in a negative sign there. Okay? Again, these are the elastic moduli. Y, the Young's modulus, S, the shear modulus, and B, the bulk modulus. Okay? And all these numbers, greater the number, stiffer the material. Okay? So that's what you want to remember. Okay, here, these tables, I'm sort of running out of time. It's 12:19. So anyway, when we do problems, I'll show you the meaning of these numbers. So whenever you have a table like this, I mean, somebody's gone to a lot of trouble to come up with these numbers. Okay, these measurements. So these are useful numbers. Okay. And again, so you saw the usefulness of pre-stressed concretes in all these structures, all the bridges that you drive over, the spans are all pre-stressed concrete. Okay, so you have these under tension, pour the concrete, let it rest, and then this span will last a lot longer than this span will. Okay? All right, guys.